Welcome to Brain Vision.
Okay, so we know the power input, which is W dot in here, can be equal to M dot times H2 minus H1, which can be also expressed as M dot times Cp times T2 minus T1. M dot is the mass flow rate of the water, Cp is the specific heat for the water, T2 is the final temperature for the water, and T1 is the initial temperature for the water. And we also know that the power input can be equal to the potential difference multiplied by the currents, which is Vi here. So therefore, if we plug in back to the equation, we have Vi is equal to M dot times Cp times T2 minus T1. And then we'll have the I, which is the current, is equal to M dot times Cp times T2 minus T1 over V. So we know the mass flow rate, which is M dot here, can be equal to rho times V dot. Rho is the density of the water, and V dot is the volume flow rate of the water. So now we can plug in back to the equation. We have I is equal to rho times V dot times Cp, and then times T2 minus T1 over V. So we know the density of water is 1 kilogram per liter, and the volume flow rate for the water is given as 0.1 liter per second. The specific heat for the water is 4180 joule per kilogram times degree Celsius. And we know the potential difference is given as 110 volts. And we know the final temperature is 30 degrees Celsius, the initial temperature is 18 degrees Celsius. So now let's plug in back to the equation to determine the currents. So the current is equal to rho V dot, which is 1 kilogram per liter times 0.1 liter per second, and then times 4180 joule per kilogram times degree Celsius, and then times 30 degrees Celsius minus 18 degrees Celsius over the potential difference, which is 110 volts. And this will give us the current is about 45.6 ampere. And this is the answer for this question.